Welcome everyone, this is Math 111Z, and this covers obviously section 4.3 in your text. So let's get started. All right, 4.3 covers the idea of what is a logarithm. What's a logarithmic function? The basic idea, well, the definition, is simply that if you have an exponential function, like a to the x equals y, then the logarithm function is the inverse of that. So we learned in section 4.1 that the inverse is when you switch the x and y, right? But this cannot be solved implicitly for y, so we make up a function that does that called the logarithm. So we say the log base a of x equals y. These two things are equivalent. These two things are equivalent. And these two things are inverse functions of each other. So if you take the log base a of a to the y, these cancel out and you're just left with y. If you take a to the log base a of x, these two would just cancel out because they're inverse of functions, and you're composing those two functions and just leave you with x. Right. You can have any base as long as, just like with bases of exponents, a has to be greater than 0. Right? We can't have a function where a is negative, and a cannot be 1. And that is simply because 1 raised to any power is just 1, so then you're just looking at a constant function, right? A constant function all the way across. Right. So let's take a look at how we would rewrite these using our newfound knowledge. So this exponential statement would say this base 3 raised to this power equals this number. True. This base 5 raised to this power 1/2 is equal to this number. This base 2 raised to this number, now look at the answers can be negative, but the base can't be negative, equals this number. True. This base a raised to this number equals b. All right, so there's this little circular motion, base raised to the number on the outside. That is how you go from a logarithmic statement to an exponential statement. All right, it says rewrite the following as logarithmic statements. Again, 3 raised to the third equals 27. 4 raised to the negative 1 equals 1/4. Right? It's asked us to go to this the opposite way. Log base 4, right? Log base 4 of 1 base to the other equals 0. Interesting enough, anything, base anything of 1 equals 0, because if you raise anything to the 0 power, you get 1. Log base 10 of 0.1, which is also known as 1/10, is negative 1. Log base 6, log, here's our base, of this is equals 1/3. Now here's a fun fact over here. If I write log base 6 of 6 to the 1/3 equals 1/3, which is true, I'm just rewriting this cubic root as a 1/3 in its fractional exponential form. Then, notice how these cancel each other out, essentially? That's always true as well. That's one we'll learn in a minute. This says log base a, here's my base. Oh, sorry, that did not go in a very nice base spot. Let's drop that down. The base is really supposed to be a subscript of v equals k. All right, there we go. We are killing this. Let's move on to our next page. All right, same thing. They want us to move these in logarithmic statement. Log base 4 of 64 equals 3. Why? Because 4 to the third equals 64. Sorry, I think I said 63, but log base 4 of 64 equals 3. Log base 10. Now, fun fact. Base 10 is called the common log because it's very common since all of our numbers are base 10 numbers. In general, we're in a base 10 system. So we often call it the common log. And if you drop it and just write the log, the 10 is implied. And that's true for most programs and most calculators. The common log of the square root of 10 equals 1/2. Also note, log base 10 of 10 to the 1/2 equals 1/2. Again, remember I talked about canceling those out? Look at this. If I took the log base 4 of 4 to the third, these kind of cancel out, and you're left with 3. So there's that inverse relationship always kind of working on those. Like us to do these without calculators. I'm going to go nice and slow. Log base 5, 125 can be written as 5 to the third. Again, those kind of cancel out. Well, they don't kind of cancel out, they do. This common log is 10 to the negative 2. So that's going to equal negative 2. Log base A of a to the fourth. What do I have to raise a to get a to the fourth? I have to raise it to the fourth. Cancel out. All right, 3, log base 3 of 5. Cancel out. Log base 10, negative 1. This, my friend, is very interesting because 10 raised to some power has to equal a negative 1. Can I multiply 10 by itself or any, fractional value of itself and get a negative number? And the answer is no. This does not exist. All right. So let's think about this graphically for a minute. Here's an exponent, 10 to the graph. See how it never crosses down into those negatives? The natural log looks like this. See how over here there are no negatives? I can't get negatives out here. Does that make sense? I can't put negatives in right here. I can't put them in. I can't put them in to the function, right? You can get them out because like here we had a negative 2, right? That's okay. Just like over here, you can put negatives in, but this inverse, you can't put negatives in. It's not in their domain. Okay, let's move back on. Evaluate the following without using a calculator. So log base 6 of 36 would be, what do I need to raise 6 to? 6 to some power equals 36. 6 squared. The answer is 2. Log base b of b to the 13. Cancels out, equals 1/3. 1/3. 10 log of 10, 9. These cancel out, we are good, 9. They're inverse functions, so they go to the inverse identity, which is just 1. Awesome. Solving equations involving logs. And here we go. So again, I'm going to say, what do I need to raise x to? For this base raised to this power equals 16. Right? That's essentially just solving this equation. 4 to the x equals 4 squared. Right? The bases are the same. The exponents must be the same. X equals 2. Right? Look at this one. 3 to the negative 2, this raised to that equals this. 3 to the negative 2 is 1/9. X equals 1/9. Right? This says base 5 raised to the 3 equals x. And that means x equals 125. Okay, a couple ways of doing this. Couple other ways of thinking about this, like this one, log base 5, x to the third. I need to get rid of an x log base 5, so I could raise both sides to the base of 5. These cancel, and then I'm left with x equals 5 to the third. Same idea. Like on this one, this is log base 3, x equals -2. I can think of taking each side with 3 as the base, putting a 3 as the base to each side. If the exponents are equal, then the number is equal. So these cancel. I get x equals 3 to the -2, which is 1/9. So there's a couple different ways of thinking about this. So maybe one way works better for you than another way, whichever makes sense. Again, common log. Common log often is not shown. That is base 10. And the natural log, which is our favorite friend, written as ln, because in France, the natural log is like el natural, so ln, like the little prefix they put in front of it in French, which is where this originated from, a French mathematician. So, or at least it was written up, the proof originally was written in French, in the French language. So this is log base e of x is the same thing as the natural log of x. We don't write log base e, we write ln of x. Okay, so this problem says using the definition, the natural log, and the graph of the exponential, which looks like this, crosses at 1 like all exponents do. Right? 1 would just be at e, which is 2.7-ish. 2 is e squared, which is 7.3-ish. And then 3 goes up to 20-ish, which is way up here, so it looks like this. They want to know, where's this 10 fall? Right? So in order for you to get like a real accurate answer, you're going to need some sort of digital graphing. You can use Desmos. I'll use a TI-84 for this. I'm going to type in, hit my y equals button, type in e to the x for my graph, hit the graph button, and then I'll hit trace, and I'll try to get close to when on the bottom, when you hit trace, there's 2, there's like an X button and a Y button. I'll try to get the Y as close to the number 10 as I can. If I can't get very close, then I'll zoom in again and try to get close to the number 10 again. So I'll zoom in until I get, if I'm on Desmos, I can actually just, you can draw the line y equals 10 on your calculator, or as well, so like you have your box, y equals e to the x in Desmos, and then you'll have another box, y equals 10, and you can look at where these intersect, right? So if I were to draw a line at 10, this is a 10 by 10, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yep. This right here where they intersect is this point that I'm looking for. On my calculator at 10.08, which seems to be about the closest I can get to 10 without zooming in again. I'll zoom in one more time. And hit trace again. At 9.98, this number is 2.3011, which is the natural log of 10, then should be approximately 2.3011. When I do that on my calculator, I take the natural log of 10 and I get 2.3025. So pretty close to what our graph is giving us. So that is how we could evaluate a logarithm graphically. I could also graph the natural log on any of these digital devices as well. All right, let's go to the next one. All right, it says check it out. Use the definition of the natural log and the graph of the exponent to evaluate the natural log of 8. So again, I would graph just on Desmos. I would take this natural log function. It looks like this. Remember I said 2 was about 7, so it's going to be just past 2 again. To get 8, I would draw up to 8. That's not even close to 8. Sorry about that. I would draw up to 8 here. Let's do that one more time, a little more accurately. Here's my natural log. At 1, it should be like there. At 2, it should be up to 7. And a little bit, it should look like this. 3 goes up. If I go to 8, looking for that number, that drops down right there. On my graph, my digital graph, I'm going to take my graph again. I'm going to hit trace, and I move over to where my graph is close to 8. My y value is close to 8. I have 8.34. I think I can get closer than that by zooming in. I have 8.03. When y is 8.03, my x value is 2.08. We'll text that on the natural log. So if I take the natural log on my calculator of 8, and I get the natural log of 8 on my calculator is 2.079. So pretty darn close there. So just an option of how you could figure that out graphically and kind of understanding the relationship between the exponential function and the natural log. Right? Now, what if you have something in one base and you want it to change it to another base? So something else like, oh, I have the log base 3 of 15. And I don't have a log base 3 on my calculator. How can I do this? So we have this change of base formula. And it says if you want to change the base, you pick your new base. It can be any number. I have a natural log on my calculator, so we'll use that. I take the natural log of whatever I'm taking of, and then the natural log of 3 on the bottom. So now on my calculator, I can go the natural log of 15 divided by the natural log of 3. Please note, and this is super important, this does not equal the natural log of 5. You cannot just reduce those in any way, okay? You can't do it. It does not work that way. So, so that is the change of base formula. Oh, let's take a look at these. It says, first one, they want us to use the common log. So the log base 6 of 15 is equal to the log of 15 over the log of 6. The log base 7 of 0.3 using the natural log is the natural log of 0.3 over the natural log of 7. Right? So these are numbers that you can calculate with any kind of standard scientific calculator. This typically is not done on any standard scientific calculator, although a lot of the newer calculators will do this. A fun thing to try, we know that, say, like the log base 3 of 9 equals 2, right? That's easy, right? We know that. Look at this. The natural log of 9, if I do this on my calculator, is 2.197224577. The natural log of 3 is 1.0986122289. Now, if I take all these digit precision from my calculator, and I go up and grab them, without like typing them in again, but actually grabbing the whole number and take that divided by that second number, I get exactly 2. It's pretty cool. Okay, so that would fall that way. All right, so let's take a look at the next page. All right. Compute the common log 16 using the change of base formula in the natural log, and show that you get the same result as in example. So, all right, so we're going to use the common log of 15 over the common log of 6. So I'm typing that into my calculator. I take the log button of 15 divided by the log button of 6, and I get 1.51139.
Alexa.
And then if I do that with the natural log, I get the natural log of 15 over the natural log of 6, typing that in my calculator. Doing it all in one line to make sure I don't get any rounding error, and I get 1.511391549, exactly the same as the other one. 391594. All right, awesome. Okay. Just taking a look at this. Just reading through some observations they have here. Although the x-axis in the table range goes from 0 to 100, they want you to just notice that the y only goes from 0 to 3, essentially, which just tells you like how condensed this is reflected, how close in magnitude these are reflected for such a wide range. As x approaches 0, the graph of the line, like as we go this way, this is approaching negative infinity. The y is going down to negative infinity, but never touches the y-axis. So this is a vertical asymptote at the line x equals 0. I think we've already covered all of these other types of observations. All right. It says graphing the natural log function. Right. So again, the natural log, the regular natural log function looks like this. All log functions look like that. If I put a negative inside, just like if I put a negative inside of any function, right, then it's going to flip over the axis like that, right? So all of the same kind of rules apply when we stretch, we shift. So remember, so this one, it's going to shift one this way. So instead of having a vertical asymptote at here, it's going to have the vertical asymptote at +1. And then this 3 in front is going to stretch at 3. So where it normally would cross the thing here at 1, it's now going to cross it at 3. Okay? And it's going to go, because it's stretching, it's going to have a stretch of 3, like that. Okay? So all of the same types of like stretches, shifts, translations, transformations, rigid transformations, and stretches all apply the same way to natural logs and exponential functions as they do to any of the other functions. All right. So this is a common log, right? Our normal common log would look something like this. I'm just sketching the shape. Not super concerned that you have like all the exact points ready. That's what we have technology for. We really don't need to graph specifically anymore. However, I do want you to really understand what the shape looks like. This negative in front is going to flip it over the x-axis. And that's the graph we're looking at now. Okay? Awesome. All right, and this is just a story problem. It gives you the equation, and you are simply going to plug in the numbers and solve where it needs to be solved. So let's kind of read through it and we'll take a look at this. Okay, since the intensities of earthquakes vary widely and are measured in a logarithmic scale as the Richter scale. So here's the Richter scale. I represents the actual intensity of the earthquake, where I sub 0 is the baseline intensity used for comparison. A Richter scale gives the magnitude of the earthquake. Because the logarithmic nature of this function, an increase in a single unit in the value Ri represents a tenfold, because we're in base 10, intensity in the earthquake. A recording of 7, for example, corresponds to the intensity that is 10 times larger in intensity than an earthquake with the recording of 6. If the intensity of an earthquake is 100 times the baseline intensity, 100 times, what is the magnitude on the Richter scale? All right. So if this is 100 times more log, and it would be 100 times the intensity, so it would be 100 over 100 times that, it would measure 2 on the Richter scale. Right? Earthquake in San Simeon, California, registered 6.5 on the Richter scale. Express its intensity in terms of I naught. So 6.5 equals the log, base 10, of I to the I naught, right? 1 over I naught, right? So we want to figure out what this would be in terms of I naught. So this is saying 10 raised to 6.5 is equal to 1 over this intensity, right? So in terms of that intensity, 10 raised to the 6.5 so remember, 100 times its intensity, relative to that intensity, was 2. So relative to this intensity, I would have to have that intensity times its baseline intensity. It would be, it would have to be roughly 3 million times the intensity of the baseline. Okay. The 2004 earthquake in central Japan was a 5.4 on the Richter scale, express its intensity in terms of the initial intensity as well. So let's take a look at that. So, and then they ask us to compare these two as well. So if that's 3 million times, roughly, 5.4, ten raised to the 5.4 would be this. And so this is roughly 250,000, right? Times, what's the ratio of this to the intensity of this quake to this? So if you take 6.5 and divide it by 5.4, you get 1.2. Right? That, if you take this number, the 3 million number, and divide it by your Japan number of the 251,000 number, you get 12.58925. Notice when I raise 10 to this power right here, what do I get? sorry. I end up getting 15.98, right? This is the ratio of the difference in intensity, this one right here, right? It's not this number, the difference between the 6.5 and the 5.4, and it's not this number, which is the ratio between this intensity and this intensity, because ratios, exponents don't work that way. It is this number right here. It is going to be roughly 16 times larger at quake intensity from the original one, because we are on this exponential scale. So there you have it. In terms of initial intensity, what is the measure 7.2 on the Richter scale? So if I take 10 to the 7.2, it would be this number. Right? Great. And then this problem is talking about the distance between planets. And notice it's using the scientific notation here with our exponents over here. Just list the distance from the sun, as well as find the common log difference of each, right? So if I'm looking at this, like trying to find the common logarithm of each distance, and this is a little jumping the gun, just a touch in some ways, right? Let's just do this two ways so that you can see how this mathematics is working, because it's kind of cool. If I take 9.35 times 10 raised to the 7th, I get this number. Right? Okay, and then this is why I think we're jumping the gun a little bit here. So that's how that works, right? What if I took the log of just 9.3 and the log of 10 to the 7th? We know this one right here is going to be 7. And if I take the log of 9.35, I get 0.9708. Look at this. They don't multiply together to give me this number. Look at this. They add. Okay. And that is demonstrating a rule of logs and logarithms that we don't know yet because it's introduced in the next chapter, but it basically says if you have the log of products, like we have here, you can calculate them by taking the sum of the two factors. So there you have it. All right, so I'm going to stop here and we will move on to section 4.4 next, where we get to learn more of these great properties of logs. Thanks so much. Bye.